Welcome to this lecture module on optics. In the last couple of lectures, we discussed about refraction through a spherical surface and then also refraction by lenses and application of this in optical instruments such as microscopes and telescopes. Today we come to the last topic on of ray optics, that is refraction through a prism, and we will also briefly discuss about the topic of dispersion. So, refraction through a prism and dispersion, that will be the topic of this lecture. First, refraction through a prism. So, here is the slide. So, what I have shown is the cross section here, top view of a prism. A ray of light is incident from here. It undergoes refraction at two interfaces, because refraction through a prism involves successive refractions at two planar interfaces at an angle. One interface like this between a denser rarer medium and the medium of the prism, and the second interface is here. The two interfaces are at an angle and refraction takes place at the two interfaces, leading to deviation of the incident light. The incident light refracts and again refracts and emerges from here. So, this is refraction through a prism. I is the angle of incidence here, d is the angle of deviation, that is angle between the original direction of the incident beam and the emerging ray here, and n1 and n2 are the two normals to the surface here, and E is the angle of emergence. A is the angle of the prism. It is actually called the refracting angle of the prism. So, whenever we talk about refraction through a prism, A is referred to as the angle of the prism. These two angles do not come into the picture, and therefore, A is referred to as the angle of the prism. BC, the lower surface here, is usually a grounded surface, which helps in blocking any stray reflections, because that is not coming into play in this part of the refraction. So, before I proceed with the refraction, let me briefly recall what I had shown, and here. So, what I am showing is the prism, and what we have seen is the top view of the prism, and the ray of light is coming from here. So, let me again show you a laser beam incident in this direction along the direction of the ray that I have. So, here is the laser beam, and we can see that the beam comes here onto the other side along the other line which I have drawn. See, the ray which is emerging ray is coming along, it is coming along the emerging ray. The ray beam, the laser beam is coming along the emerging ray after refraction through the prism. So, this is the, here is the input beam. As you can see, if I block, then there is nothing coming out there. So, there is the input beam. There is no laser beam coming from here. A small amount of reflection is coming here, but the major part of the light beam is refracted through the prism and comes along this line here. So, if you change the angle of incidence here, the angle of emergence will also change. I am just showing you the angle of changing the angle of incidence, and the angle of emergence also changes here, right. So, we will come back to the discussion on refraction through the prism. So, I have already discussed each of these quantities here, and let me proceed further now. So, refraction through a prism. So, this time I have shown slightly a bigger prism here to make the angles very clear. So, let us see here, right. So, first see the prism. The incident ray undergoes refraction here. This is the direct path of the ray if the prism were not there, and this is the deviated ray, and emerging ray, and therefore, this is the angle of emergence. So, what we can see here is angle theta 1 plus angle theta 2. So, the total angle of deviation d is angle up to this and from here to here. From here to here it is theta 2, that is shown here, and here to here is what is shown here as theta 1. So, d is equal to theta 1 plus theta 2 in this diagram. Now, what is theta 1? Theta 1 is I minus r 1. There is r 1 here. R 1 is the angle of refraction at this interface, and r 2 is the angle here, which is actually the angle of incidence from this direction, but would become angle of refraction if light ray was to be incident from this side. And therefore, this whole angle is I, and therefore, theta 1 is equal to I minus r 1. Similarly, theta 2, the angle theta 2 here is this is the emergent ray. So, emergent angle E is here. So, this is entire angle is E, emergent angle. R 2, this is R 2. So, the opposite angle there is R 2, and therefore, theta 2 is equal to E minus R 2. So, we have I minus R 1 plus E minus R 2, or I plus E minus R 1 plus R 2, that is the angle of deviation. But if we look at this quadrilateral here, then we can see that this angle is 90 degree, this angle is 90 degree. I am looking at AQMN, AQMN. Note that this is the normal, and therefore, angle AQM is 90 degree, angle ANM is 90 degree. So, the sum is 180 degree. That means, angle A plus angle M or angle QMN must be 180 degree. So, angle A plus angle QMN is equal to 180 degree. But in this triangle, looking at the triangle QMN, angle M plus R1 plus R2 is also 180, and therefore, R1 plus R2 is equal to A. R1 plus R2 is equal to A, the angle of the prism. So, we can substitute in this equation here, and therefore, we have A is equal to R1 plus R2 and D is equal to I plus E minus A. So, we call this as equation 1 and 2. N2 is the refractive index of the prism, and N1 is the outside medium, refractive index of the outside medium, which is usually air outside. Now, this is when the ray comes in this direction and goes and refracts and emerges out from here. What if the ray were to be incident from this direction along this path? The reversibility of light says that the ray would trace the same path again. So, let me show this slide here, and we see the reversibility of light. So, we see that if the ray were to come from here, that is, if this would have been the incident angle, then at this point again the Snell's law would be satisfied, and the ray would follow the same path, and then it will again satisfy the Snell's law and follow the same path here, which means if I is the angle of incidence when incident radiation or incident ray is from here, then E would have been the angle of emergence. However, if the ray were to be incident from here at an angle E, then I would be the angle of emergence. In both cases, what we see is whether the ray is incident from here or the ray is incident from here, the net deviation is the same, d, it is identical, and therefore, here E goes over to I when the ray reverses from in this direction, reversing the direction of the incident ray, E goes over to I, then I will go over to E. But no change in D, D is the same in both cases, as you can see they are opposite angles here, and D is equal to I plus E minus A. Here also we can see that if we put I plus E or E plus I, it is one and the same, D remains the same. Therefore, if we reverse the direction of propagation of the ray, I and E would get interchange, but D remains the same. this indicates that for two different values of I, because I and E, D is the same, but I and E can be different. Only thing that we have said is when I becomes E, E becomes I, but I and E may be different, and therefore, for the same value of D, we will have two different angles of incidence. For two different values of I, D will be the same. Therefore, there must be a point of degeneracy, that is I is equal to E. This is our conjecture. We will see what we get. Now, coming back to the problem and calculating the angle of deviation here. So, D versus I. We are now interested in determining the angle of deviation versus the angle of incidence. We have the Snell's law at this interface and this interface. At the first interface, so this is the first interface, I have shown a small diagram now. First interface, sin I by R1, R1 is the angle here, and therefore, sin I by sin R1 is equal to N2 by N1. Snell's law applied to this interface, and Snell's law applied to this interface gives sin R2 by sin E, because angle of incidence here is R2, angle of emergence is here the refracted angle. So, sin R2 by sin E is equal to N1 by N2. N1 is now the second medium, outside medium, N1 by N2 for the second interface. Therefore, for a given prism, N2 and A are constants. The material of the prism has a certain refractive index N2 and a angle A here. They are known for a given prism, and therefore, for each angle I, we can calculate R1, because we know N2 and N1. So, using Snell's law we can calculate R1. Once we know R1, we know R2, because R1 plus R2 is equal to A, and once we know R2, we can calculate E, because we know N1 and N2. Sin R2 by sin I is equal to N1 by N2. So, for each angle I, R1 and hence R2 and then E can be determined, which implies that angle of deviation D can be calculated for each angle of incidence. As discussed earlier, by the reciprocity of light propagation, I and E are interchangeable, which means for each D there will be two values of I. So, let us plot this for a typical case of D versus I. So, here, so I am showing a graph here of D, the angle of deviation versus I. So, typical angles. So, what is shown is a qualitative plot of D versus I, D angle of deviation versus angle of incidence for a typical prism of A is equal to 60 degree and N is equal to 1.5. This is how it looks. So, what is to be seen is, as I increases, for any value of D, we can see that there are two values of the angles of incidence. When this is I, this will be I E, and when this value is I, this will be E. So, for each value of D, there are two angles of incidence. So, if we come down, however, there is a point here where it becomes minimum, the deviation passes through an extremum here. So, this is minimum. At that point I is equal to E, because there is only one value of the angle of incidence, and the corresponding angle of deviation is called the angle of minimum deviation. If you start from one end, go on increasing I, then the angle of deviation will come down initially, come down to a minimum value, and then it will again start increasing, and this angle of minimum deviation is designated by dm. The point is, at this value of dm, I is equal to E. For all other values, there are two values of angles of incidence, whereas at the angle of minimum deviation I is equal to E. So, substitute now, therefore, D is equal to I plus E minus A, dm is equal to 2 I minus A, because I is equal to E. So, it is 2 I minus A, or I is equal to A plus dm by 2. the first equation, I is equal to A plus dm by 2. So, now let us look at when I is equal to E, R1 is equal to R2 is equal to R. If I is equal to E, so if we look at the diagram here, when I is equal to E, that means if I is equal to R, an angle of incidence I gives an angle of refraction R1, then an angle of incidence from this side which is E will also give the same angle of refraction R2 which is equal to R1, because the refractive indices are the same N1 and N2, N1 and N2, and therefore, R1 must be equal to R2 if I is equal to E. So, at the angle of minimum deviation, what we have is R1 is equal to R2 and we call it as R, and therefore, from R1 plus R2 is equal to A, we have R is equal to A by 2. So, we have two equations here, A plus dm by 2 is equal to I and R is equal to A by 2. Now, using these two equations 1 and 2, we apply the Snell's law, sin I by sin R is equal to N2 by N1. Substituting for I and R from 1 and 2, we have sin A plus dm by 2 divided by sin A by 2. Usually, of course, the N2 is the refractive index of the prism, N2 here is refractive index of the prism, and N1 is the outside medium, and usually outside medium is air, and therefore, N1 is equal to 1 and N2 is equal to n, where n is the refractive index of the medium, and therefore, we write, therefore, we get the formula for refractive index of a prism as n is equal to sin A plus dm by 2 divided by sin A by 2, where A is the angle of the prism and dm is the angle of minimum deviation. This is an important formula and it is used in practice to determine the refractive index of the material of a prism. An important experiment which is used to determine is with the experiment with a spectrometer. So, this is although not a part of our course, but I would just like to show that to impress upon you that the angle dm of minimum deviation is a measurable quantity, and therefore, we can determine the refractive index very accurately. Using a spectrometer comprises of a collimator which sends a collimated, that is a parallel ray from here, and then the ray passes through the prism which is placed on a prism table. This is the top view looking from the top. So, there is a prism table on which you place the prism, and light passes through the prism, refracts, and the refracted light is detected by seen by a telescope. There is a telescopic arm through which you can observe the refracted ray. So, using this arrangement, one can determine the angle of minimum deviation. Practically, one can measure the angle of deviation, and of course, the angle of prism A can also be measured, and the refractive index of the material of the prism can be determined using this formula very accurately. So, this is the importance of this formula which we have derived, and there is no approximation involved. We have not made any approximations in deriving this formula. Now, for thin prisms, so this is for normal prisms, but for thin prisms the angle A is very small. Thin prism means the angle A is very small. I have shown here it is a thin prism, A is very small, and of course, the thickness of the medium is also very small, and therefore, the D is also very small, because the thickness of the medium is very small, it is quite thin, and therefore, the angle of incidence is very small, angle of refraction is very small, and therefore, we see that the angle of deflection or deviation here is very small, because A is very small, and therefore, n which is given by this formula that we have derived, can be approximately written as the sin theta can be approximated to theta, that is a plus dm by 2 divided by a by 2 when a is very small, which is equal to 1 plus dm by a. We can divide this and see that this is 1 plus dm by a. In other words, dm, the angle of minimum deviation, is equal to n minus 1 into a. We can clearly see that when a is very small, dm is also very small. So, the formula is quite useful when a is very small. One can immediately determine dm. Now, there can be several solutions, several problems, several examples which can be worked out based on the Prism formula, that is n is equal to sin a plus dm by 2 divided by sin a by 2, various situations. Okay. So, let us take an example of refraction through a prism. So, let us see this. Consider a glass prism of equilateral triangular cross section and refractive index 1.6. Refractive index of the material is 1.6. What should be the angle of incidence on the refracting surface for a ray, so that angle of incidence equal to angle of emergence? Second part, if the prism is immersed in water, refractive index is given, n is equal to 1.33, what would be the angle of minimum deviation? So, let us try to understand this problem. So, consider a glass prism of equilateral triangular cross section. So, let me write the or draw the diagram here. So, we have a glass prism of equilateral triangular cross section. So, this is actually the top view as we have seen in the actual prism. So, equilateral. So, the information given is angle A is 60 degree. There is a ray of light which is incident here and it refracts and emerges out from the other side. The question is, so this is the normal here and the normal here. So, what the first part is, so the refractive index is given n2 here 1.56. If the refractive index of the outside medium is not given, then we assume that n1 is equal to 1, that is air, because in general the prism is placed in air and therefore, n1 is equal to 1. So, the question is what should be I, so that I is equal to E. So, this angle is the angle of emergence and here is the refracting angle R1 and this is R2. So, R1, R2, A the angle of, so given N2 is equal to 1.56, A is equal to 60 degree. So, the first part of the question is what should be the angle of incidence, that is I, for a ray, so that angle of incidence is equal to angle of emergence. So, I is equal to E. So, I is equal to E. I is equal to E implies R1 is equal to R2, R1 is equal to R2 is equal to A by 2. We have already seen this, because if I is equal to E, that means R1 must be equal to R2, because it is the same interface, same refractive index separation here, and I is equal to E, and therefore, R1 must be equal to R2, and then this will be equal to A by 2. We have already seen this, because this is 90 degree, this is 90 degree, therefore, A plus this is equal to 180 degree, and R1 plus R2 plus this angle here, that is if I extend this angle here will be 180 degrees, and therefore, R1 plus R2 must be equal to A, and therefore, R1 is equal to R2 is equal to A by 2. Because A is 60 degree, we have this is equal to 30 degree, R1 is equal to R2 is equal to. the question is what is I? We know refractive index here, we know the refractive index here, we know the angle of refraction here, and therefore, we can determine I simply by applying Snell's law, that is sin I. So, for the first part applying Snell's law, sin I divided by sin R 1 is equal to n 2 by n 1. So, n 2 by n 1 which is equal to 1.56 divided by 1, because n 1 is 1. So, R 1 is 30 degree, therefore, sin R 1 is half, that is 0.5. So, here, so let me take it further, therefore, sin I here is equal to 1.56 into sin 30 degree, sin R 1 sin 30 degree, which is this is half, and therefore, this is equal to 0.78, and therefore, I is equal to sin inverse of 0.78. Of course, you need a calculator to get the angle, but the numbers can be chosen in such a way that you sometimes do not need a calculator. So, this can be calculated and we get this as equal to 51.26 degree, 51.26 degree. I is equal to, that is this angle here, I comes out to be 51.26 degree. So, this is the first part, that what should be the angle of incidence, I is equal to E. Of course, we can determine the angle of minimum deviation dm. So, dm is equal to twice I minus A, twice I minus A, that is how we got I is equal to A plus dm by 2. So, dm, that is the angle of minimum deviation in this case. In the first part of the question dm is not asked, but we can just calculate for interest that this is equal to, so 51, so 102.52 minus A, that is 60. So, this is equal to 42.52 degrees. This will be the angle of minimum deviation in the first case, but that is not asked in the question. In the question we have angle of minimum deviation for the second part. If the prism is immersed in water, what would be the angle of minimum deviation? So, how can we work out? Exactly like that is the same prism. So, here, so we can again draw the prism, but this time the outside medium is, so the ray is here. So, everything remains the same except that this is now 1.56, but outside medium is 1.33, all other things remain the same. If the prism is immersed in water, what would be the angle of minimum deviation? So, now we have, so how do we go about this? So, we can again apply Snell's law, because I is equal to E is the condition which gives us R 1 is equal to 30 degree independent of what the medium is, but if the outside medium is 1.33, the Snell's law will be sin I by sin R. So, in this case I apply here, it is sin R 1. So, this is equal to n 2 by n 1, n 2 by n 1, which is equal to n 2 by n 1, which is equal to 1.56 divided by 1.33. So, R 1 is 30 degree and therefore, sin I is equal to, so this is half. So, 1.56 divided by 1.33 into half. So, 1 by 2, so 2. So, that is equal to, so this is 0.78 by 1.33. So, 0.78 by 1.33. So, we will substitute this. So, I is equal to 0.78 by 1.33, and therefore, I is equal to, so I is equal to sine inverse of 0.78 by 1.33. So, if we use a calculator, we can find this out as 35 point. So, now the angle has reduced 35.90 degree. Therefore, the angle of minimum deviation. So, in this question we have angle of minimum deviation is equal to twice I minus A. So, that is equal to 35.9 into 2. So, that is 71.8 minus 60 degree here. So, that is equal to 11.8 degree. So, 11.8 degree. So, why I had calculated dm in the earlier case was because we got dm is equal to, so the dm that value that we got earlier was 42, here it is. So, dm was 42.52 degree, but now the dm is 11.8 degrees. Obviously, it is understandable if we see the figure that if the refractive index here is 1.33, then the refraction will be much smaller. If I has to be equal to E, I has to be much smaller, because the refractive index difference is much smaller. That is how we have got I is equal to a smaller number 35.90 and the deviation is equal to 11.8 degree. Of course, we could have also used the other formula. We could have used the formula for refractive index. So, we had N21 is equal to N2 by N1 is equal to sin A plus dm by 2. So, sin A plus dm by 2 divided by sin A by 2, and we will get exactly the same answer, sin A by 2. So, in this case we know that N2 is given. So, 1.56 divided by 1.33 is equal to sin of A is known. So, A by 2 is 60 by 2 is 30 plus dm by 2, so dm by 2 divided by sin 30, which is half. So, half goes there and we will have the same expression again, that 1.56 divided by 1.33 into 2, half. So, it is into 2 here is equal to sin 30 plus dm by 2. So, if you simplify this, so we take the inverse of this. So, sin inverse of 1.56, that is by 2 is 0.78. So, it is 1.33 into 2 is equal to 30 plus dm by 2. So, we can bring this to this side and we will get the same answer. So, calculate dm is equal to 11.8 degrees as before, 11.8 degrees. So, either we could use this formula, it is not necessary that we have to use the same formula. So, in this case, once we identify the picture, once we have recognized the picture, then it is possible to simply apply Snell's law here. We need not go to the other formula of sin A plus dm by 2 by sin A by 2, and that is what I have shown through this example. And let me take up the next topic, which is dispersion. So, dispersion. So, it is the fascination with a glass prism. The most, when we think of dispersion, the first impression is that white light incident on a prism disperses into different colors. That is the first impression that we have when we talk of dispersion or when we talk about the prism. So, what is shown here is incident white light which disperses, that is which spreads out into its component wavelengths. White light comprises of large number of wavelengths or almost a continuum of wavelengths. We know that the visible radiation has wavelengths ranging from 400 to 750 nanometers, and white light, when the visible white light, when it is passed through a prism, it disperses or spreads out into its component colors, and the colors come in this order, that is violet, indigo, blue, green, yellow, orange, Vibgyor. So, violet bends the most and red bends the least here, and in between we have a colorful spectrum, color ranging from red to violet or violet to red in this direction. So, this is called a spectrum, that is it is called the white light spectrum, Vibgyor. So, varying from violet end around 400 nanometer to the red end around 650 or even 700 nanometer. So, this is what we call as dispersion. Now, why does this happen? Why does dispersion happen? So, let us discuss this in a little bit of detail. So, here dispersion. Dispersion happens because refractive index of a material depends on the wavelength of light, that is n is a function of lambda, n is a function of lambda. Now, let us take some examples and discuss it further. The widely used materials in glass prisms are crown glass, flint glass and fused quartz, that is silica, pure silica. So, these are the widely used materials in making glass prisms. The variation of refractive index n with wavelengths is shown in the next slide. So, I have already plotted this variation, qualitative plot of the refractive index variation with wavelength. So, we can see here n refractive index versus wavelength. We can see that in all cases n is continuously decreasing as wavelength is increasing. So, the refractive index decreases with wavelength for all the three materials. The actual value of the refractive index is different for the three different materials, but the refractive index varies with wavelength in the same fashion, but the rate at which the refractive index changes will be different for different materials. So, that is called dispersion. Dispersion for different materials will be different, but qualitatively refractive index decreases as wavelength increases. So, this is what is called dispersion. So, let me give some typical numbers, values here, so that we have an idea what is the change in refractive index as we go from blue color to the red or vice versa. So, here in this table I have noted down the refractive index values for at 4 different wavelengths. Actually, these 3 wavelengths are from the hydrogen spectrum, lines corresponding to the hydrogen spectrum, and this is the sodium line 589.3 nanometer is the sodium line. So, fused quartz, the refractive index values, so it is highest for violet 1.470 and keeps on decreasing 463, 458, 456. The change is not much, but it is continuously decreasing. You see the same thing for crown glass 1.533, 523, 517 and 515, and for the flint glass 1.663, 639 and so on. We can see that the maximum change is approximately 0.041 here, whereas the maximum change here is 0.014. This is 0.041 a change. So, 1663. So, 663 to 222. So, 22, that is 63 to 22 is 41, whereas in this case 70 to 56 it is 14. We can see if I keep back the diagram, the refractive index change is large as I go from here to here for flint glass, but for fused quartz the change is very little, it varies very little. That is what the numbers also tell us. Now, the variation of refractive index of a material follows approximately 1 by lambda square dependence. So, if I were to plot the variation of refractive index, that is n versus lambda, then for most of the materials the refractive index varies like this, it is continuously dropping down. Here it is n and this is lambda. The relation is given by, this is approximately proportional to 1 over lambda square. This was experimentally observed, and then Cauchy gave a formula which is called Cauchy's formula, Cauchy. So, Cauchy's formula, n of a material is n of lambda is equal to A plus B by lambda square, where A and B are constants, A comma B are constants. Constants for a given material, they are not universal constants, constants for a given material, They are also called Cauchy's constant, A and B are called Cauchy's constants. Now, let me go further. Before I come further, I want to talk about one topic which is called dispersion compensation. Dispersion and dispersion compensation are very important and huge topics. But let me just introduce you to dispersion compensation in its simplest form. So, what is shown here is a prism here, white light entering a prism which leads to dispersion, that is spreading of the component lights which are entering, now it is coming here. If we place another prism inverted as I have shown here, it could be of the same material or it could be of different material, usually a different material and different size is used for certain reasons which is beyond our scope of discussion here. But what we can see is that the spreading is compensated by the second prism, the inverted prism compensates for the spreading because this was bent more in this direction. Now, the second prism bends it more in the other direction, whereas red had bent less, but also it is bending less. The net effect is both of them combine here to form the white light again. In other words, we started with white light and using the first prism the way components were dispersed, dispersed means they are spread. Now, the second prism, because it is inverted, it combines so that we get back the white light. So, by choosing a second prism of appropriate size and refractive index, it is possible to compensate for the dispersion of the first prism. So, this is in simple terms what is meant by dispersion compensation. I want to take one example from nature, and that is formation of rainbows. So, formation of rainbow, this is an effect because of dispersion of the different colors. The formation of rainbow, which most of us have seen just after the rains, if the sun comes out and we still have water droplets in the air, and then there is a possibility that we might be able to see rainbows. Otherwise, of course, near great waterfalls, big waterfalls like the Niagara waterfall, where water pours down from a large height, huge quantity of water continuously pouring down, leads to water droplets sprayed upwards, and whenever there is sun, there is a possibility of seeing rainbows. Almost every time one can see the rainbow if sun is present at the right angle. So, what is shown here is these are the water droplets. I have shown it a little bit bigger. This is the water droplet. Light, sunlight is coming, a ray of light is representing here. White light enters the water droplet, it disperses, red and blue separates out, it undergoes total internal reflection because outside it is air and this is water. So, it is denser to rarer, and if the angle is such that this angle is greater than the critical angle, then it can undergo total internal reflection and then it refracts out. Now, in the process as illustrated in the diagram here, we can see that red comes at a larger inclination, the inclination angle with the horizontal. So, I am talking about the inclination angle with this horizontal. So, red comes out at a larger inclination and blue comes out at a smaller inclination, and therefore, because of the refraction, the dispersion which is taking place inside the medium, and therefore, an observer, here I have represented an observer's eye, an observer sees red at a higher angle because it is at a larger inclination. So, for him it appears as if red color is coming from a position somewhere here in the horizon and blue color comes from a lower position in the sky, and therefore, we see red, yellow, green, blue in this order. The rainbow colors are visible in this order if the situation prevails like this. There are situations when the color may interchange depending on if there is a second refraction undergoing, that there is a possibility of interchange of colors. But the formation, the point in this is the formation of rainbows is because of dispersion taking place in the water droplets, dispersion of sunlight taking place in the water droplets near waterfalls and soon after rain. So, I will observe red color, it is depending on the size of the water droplet, it can be shown that the red color has a net deviation of 42 degrees, while blue undergoes a deviation of 40 degrees. So, therefore, blue becomes more horizontal and red becomes more inclined, and when you see from here, red goes up and blue stays below in the sky. So, I will observe red color making a higher inclination with the horizon will appear at the upper part of the rainbow. Now, I have brought in, I have just introduced the topic of dispersion at the most elementary level, the first level. Now, if white light was undergoing dispersion when it passes through a prism, why did not we talk about this earlier? We have discussed refraction through a prism, refraction through a lens, reflection and at a mirror. Nowhere we have talked about dispersion. What is the effect of dispersion in the discussions that we had earlier? So, let us look. First refraction at the prism 1. In the case of prism, I am discussing what is the effect of dispersion in the discussions that we had. We derived, so here is the prism and this was the angle of incidence, and here the refracted ray, and then we had this angle of deviation d, angle A and refractive index of the prism, and then we said n is equal to sin A plus d by 2 A plus d m. Actually, this is true for angle of minimum deviation d m by 2 divided by sin A by 2. But we said n is a function of lambda. and therefore, strictly speaking, so A is a constant and therefore, the deviation here dm is also a function of lambda. And this formula is strictly correct only for a given wavelength, one lambda. It is correct for one lambda. In other words, if we measure the minimum deviation for a particular wavelength, that is for blue color or yellow color or red color, then we can determine the corresponding refractive index at that wavelength. So, if I measure dm for blue, then I would get nb, that is n of lambda for the blue color. So, n of blue, n for the blue color will be equal to this if I measure dm at blue. So, in the case of a prism, in this discussion, the discussion is strictly true for a particular wavelength. But normally, we consider the yellow light of sodium yellow light and assume that all the discussions that we have are for yellow color. But otherwise, this formula is true for a particular color or a particular wavelength only. Now, in the case of thin lenses, we have next considered, before that we have considered thin lenses. So, 2 in the case of thin lenses. Thin lenses, observe that I have deliberately shown it very thin now, thin lens, the angle. So, the angle here is very small. If I break this into segments, then the top segment looks like a prism, but A is very small, A is very small. Even in other cases, if I have a segment like this, then of course, it is part of a prism where the A is very small. I am using only the ray, I am using only here. So, refraction, undergoing refraction and then undergoing refraction. But A is very small and therefore, we have D is equal to n minus 1 into A. We have derived this for thin prisms, D is equal to n minus 1 into A. If A is very small, deviation is very small. What it means is, although n is a function of lambda, so strictly speaking this is n of lambda minus 1 into A. Therefore, D of lambda, D will have a dependence on lambda. However, D itself is very small if A is very small, and therefore, the dependence on n lambda is very small. In other words, the difference, so D for blue color minus D for red color, this difference will be very small, because D itself is very small in the case of thin lenses. That is why we have considered thin lenses. And third, in the case of mirrors, our first discussion were with mirrors. In the case of mirrors, there is no dispersion. Why there is no dispersion? Because light does not propagate through the mirror, it is reflected from the mirror, and therefore, there is no defect. Light is only for dispersion, light has to propagate through the medium, whereas in the case of mirrors there is no dispersion, because light is only reflected from the mirror. Light is reflected. We assume that it does not enter the mirror, and therefore, dispersion does not affect in these two cases, but indeed dispersion is an important issue in the case of a prism. Finally, as I mentioned, dispersion is a huge topic. It is not just in optics, it is important in various branches of physics and also in engineering. What it basically means is whenever a system's output or system's performance or system's characteristics depend on the frequency. We have discussed about wavelength because it is convention to deal with wavelengths in the case of light because of convenience of the numbers, but wavelength or frequency are interchangeable, and whenever a system's characteristic is frequency dependent, there will be dispersive effects or dispersion. This is a very important topic, but every time dispersion is introduced from dispersion of white light, the colorful spectrum, the Vibgyor spectrum of white light that one see when light passes through a prism.